Okay, welcome back everybody. Good morning. So today I'm trying to read along the topics about data leakage. This is kind of the final session of the intermediate machine learning, the courses from Kaggle. I've kind of read through like really fast. It's kind of uh, for me it's kind of difficult because it's kind of like very nuanced. So we'll see. Okay. Let's see how far can it go today. So all right, I'm just gonna read this one by one. Make it bigger first, probably. Is it better? Okay. So in this tutorial, we will learn what data leakage is and how to prevent it. Right? Okay. If you do not know how to prevent it, leakage will come up frequently, and it will ruin your models in subtle and dangerous ways. So this is one of the most important concepts for practicing data scientists. Uh, Basically, it's trying to make your data more uh, generalized instead of underfitting and overfitting. Just a quick recap if you forget about the overfit and underfit. Basically our model is basically a mathematical function, right? So we want our mathematical function to be generalized in quote. We don't want it to be underfit means the mathematical model is too kind of too simplistic for the problems you are trying to solve. For example, if you're trying to solve a housing problem, then probably we can think of, I don't know, if we ask a domain expert in the how to predict a specific house, then probably he or she will say like, oh, there's like 100 factors, or at least 100, that determine the whether that house is worth 100,000, 200,000, 300, or 1 million, right? But when you develop the model, it turns out your algorithm is kind of too simplistic, meaning you can only capture, for example, 20 different features. So it's too simple and it's called underfit, right? Um, and the opposite of that, the model is overfit, which is basically kind of the opposite of that. So you have a mathematical function or your model is too complicated. Or another way of saying it, too complicated could be means that your mathematical function is too big. There are so many variables instead of you only probably enough to put just 100 variables, but the mathematical can capture, let's say, 1,000 variables or more than that. And or when you train the model, even though probably, for example, you already get the appropriate model that needed for that particular problem, right? But when you train the model, you train it in such a way that the hyper the weights and oh sorry the I'm using the term from deep learning, but the variable for that particular model. Remember, when we train or fit the model, basically what you're trying to do is to find the variables, right? So for example, if you have 100 variables for housing, you have A to, for example, to Z, which is 27. Sorry, 27. I'm giving a bad example here. So you're trying to find whether A is zero point 0.5 or B is zero point 0.7 and C is zero point 0.6, D is negative 100, and so forth. Right? You have to find all the different numbers, right? So that your mathematical function is like uh, be able to predict, right? But if, for example, if it's overfit, which means that your model, when you fit or train the model, you get the parameters, which is, I'm talking about the A to Z, which is, yeah, we're talking about 27 different parameters. That parameters only fits only good for the data that you train for. So for example, you have a data set for 1,000 training data set. So when you train it, it gives you a good result, like high accuracy, 95%. But when you and then you validate it, right? And you validate it, it's still giving you a good result. But when you deploy it in the real world and when you test it, it gives you a really different answer. For example, the accuracy drops to like 80%. So which means your model is kind of like overfit only for that particular data. Which also means that your data is not being represented, right? It's not, it's kind of, we can call it this bias. So this data leakage has to do with that. So we'll see how it's going to be like. There is some subtlety there. There's some kind of differences, nuance. But the idea is like that. Just trying to make the model or um, um, generalizable. Okay, so uh, data leakage or leakage happens when your training data contains information about the target, right? So your training data contains information about the target. So for example, if you have the housing target, so your training data has all of the features um, necessary to predict the sale price, right? If you want the target to be the sale price, right? But similar data will not be available when model is used for prediction, right? So, so for example, you have hundreds of features during training, but when you use it for prediction, actually in the real world, um, um, you only have like 50 or 70 features. So 30 of the features are not being used, right? This leads to high performance on the training set. So high performance on the training set and possibly even the validation data, but the model perform poorly in production when you deploy the real world. So um, this is like I said, it's the case for overfit. So I don't know what's the difference between data leakage and overfit, right? It's kind of like the same, but hold on, we're gonna read this through, right? But just from this definition, this is kind of the same definition of the overfitting, right? Because it performs really good, accurate during the training and or perhaps during the validation, but when you deploy it in the real world, it performs poorly. In other words, leakage causes a model to look accurate until you start making decisions with the model, and then the model becomes very inaccurate. Okay, so there are two types of leakage: um, target leakage and train test contamination. Let's see what's the difference. So for target leakage occurs when your predictors include uh, data that will not be available. So your predictors means your algorithm, I think, include data that will not be available. Again, let's say, for example, we already trained the algorithm, and the algorithm, the predictors um, can take in 100 features, right? But this data is not available at the time you make predictions. So when you make that predictions, um, those 100 features or only some are available, right? It is important to think about the target leakage in terms of the timing or chronological order that data becomes available. Okay, so you think about the timing. So when you're training, it's like zero timing, and then after that you do the validation. It's like um, time one, and then after that you could say probably time two is the predictions, right? Before you deploy it, right? But that's when you kind of deploy it in the real world. Not merely whether a feature helps make good predictions. Okay, so you have the in terms of the timing and chronological order. An example will be helpful. Imagine you want to predict who will get sick with pneumonia. So the top few rows of your raw data look like this. So you have three, three, let's say three data set, right? This row number one, row number two, row number three, right? And it has what, one, two, three, four, five columns, right? And this is trying to predict whether, um, given these features, so there's one, two, three, four, so four features, which is age, weight, male, or not, and took antibiotic medicine, false or not. Given that features, you can predict whether that person has pneumonia or not, right? So it says here, people take antibiotic medicines after getting pneumonia in order to recover. So if I got sick, for example, pneumonia, then um, I have, I have to take the antibiotic medicine, right, to recover. So that's kind of straightforward, right? So if I got sick, I have to take medicine, right? So this is what it's saying. So if they don't get sick, they don't take medicine. They don't get sick, they don't take medicine, right? If they get sick, which is true, then they have to take the medicine, right? So the raw data shows a strong relationship between those columns. But took antibiotic medicine is frequently changed after the value for gut pneumonia is determined. So, okay, so this column, the value is frequently changed after the value of gut pneumonia is determined. I'm trying to understand why is that? So if you determine that that person is, um, let's say, sick, um, it doesn't get frequently changed. Okay. This model would see that anyone who has a value of false for took antibiotic medicine didn't have pneumonia, right? Since validation data comes from the same source as training data, the pattern will repeat itself, and the model will have great validation, cross-validation scores. Okay, but the model will be very inaccurate when subsequently deployed in the real world because even patients who will get pneumonia won't have received antibiotics yet. Because even patients who will get pneumonia won't have received when we need to make prediction about their future health. Okay, so if there is a patient um, can get pneumonia, won't have received antibiotics yet. So because we are going to deploy this in the real world, right? So and then so for example, we ask patient one, so age 65, weight 100, male, right? And then he doesn't take antibiotic medicine, right? And then it's trying to predict, will it get pneumonia? Um, According to the algorithm, because the algorithm is already being trained. If he didn't take medicine, that means he didn't get pneumonia. But in the real world, that doesn't happen because, for example, if they ask me, okay, I'm whatever, 50 with 140, I'm male, right? False. Did I take antibiotic medicine now? I said no, right? And then the algorithm will predict I wouldn't have pneumonia, but that's kind of false because even though I didn't take the medicine right now, I would still have a chance, right? To get pneumonia, right? So I hope you're clear there because um, um, it doesn't mean that if I don't take the medicine right now, it doesn't mean that I wouldn't get it. I would still get it because this data is just mean the history data just means that If you get pneumonia, then you take medicine. If you don't get pneumonia, then you don't take the medicine. But it doesn't means that relationship. It doesn't means the other way around. It doesn't means that if I don't take medicine, then I won't get pneumonia. It doesn't mean that if I take the medicine now, I would definitely get pneumonia. So I think what I'm trying to say here, or what this trying to say is the relationship is not vice versa. So um, so because over here, if we put this in the algorithm, it seems okay. It seems the cause, if you look at just the causal relationship, um, uh, the algorithm will catch the causal would be if you get pneumonia, then the effect would be you take the medicine. If you don't get pneumonia, then you don't take the medicine, right? So the cause is good pneumonia, the effect is antibiotic medicine, right? Or in that sequence, even though there is no casual relationship, you could say probably just there's a correlation, but the sequence is you have you have to get sick first, or you don't get sick, and then you do something with the medicine. But you cannot infer the opposite. You cannot, the sequence cannot be um, cannot be rotated, cannot be how do you turn upside down? So you cannot say um, if you take the medicine, therefore uh, you don't have pneumonia. No, not necessarily, because even though if you take medicine, you still can get pneumonia. Or another way of saying, if you don't take the medicine, then 100% you wouldn't get pneumonia, right? Which is not true, because even though you don't take the medicine, you could still get pneumonia, right? So this is called target leakage. Yeah, it's kind of, that's why I'm saying when I read this, kind of confusing. How do I make sense about this? But when they say it, it's just when your predictors include data that will not be available at the time you make predictions. So this is what it means. It means the relationship is not being, how do you say it? It's not being um, the same. Yeah, because over here the pneumonia, it seems, is the first sequence, and the antibiotic is the second, or the pneumonia is the casual, and the antibiotic is the the effect. But you cannot put it. It doesn't work the opposite, right? So that's called target leakage. So it's kind of tricky, this one. You kind of like really think. Yeah, I hope you understand. Let me know if my explanation is not is wrong, or has to be like uh, corrected, or is there a better way to explain it, right? Using a different probably sentence of wording. But that's the way I understand it, at least for now. Okay, that's why. Okay, so well, let's move on. So okay, so the model would see that anyone who has a value of false for took antibiotic medicine didn't have pneumonia, since validation data comes from the same source. Okay, but the model will be very accurate when subsequently deployed in the real world, because even patient who will get pneumonia won't have received antibiotics yet when we need to make prediction about their future health. Yeah. To prevent this type of data leakage, any variable updated after the target value is realized should be excluded. So how do you do this? So I don't understand this one. So any variable updated after the target value is realized should be excluded. So usable, and then the moment of prediction, you cannot use it. Hmm. So how do you do this? I don't get it. Any variable updated. after the target value is realized. Hmm. So that's during training. This is for during training, and this is the moment of prediction. Should be excluded. Hmm. Because even patients who will get pneumonia won't have received antibiotics yet when we need to make predictions about their future health. So how do you do this? Like, do you exclude this? Do you still include it? When you include it, it will make that causal relationship, right? Imagine you want to predict who will get sick with pneumonia. Hmm. Yeah, I don't know how to. I'm not sure about this. Let's just be aware of this because I'm thinking you can put more data, but if all of the data is like that, then probably you cannot use that algorithm because the data is kind of like false. I mean, I mean, or you can put a caution on the algorithm under what circumstance you can use the algorithm for, right? Because it seems this data, the way I see it, is being generated uh, for the people who got sick already or who didn't get sick. Yeah, I don't know if you ask like 100 participants or 1,000 participants, um, it has to be the questions because yeah, you ask the question, you take antibiotic medicine, is that before or after, right? This has to be like this is like after. You can put rearrange these features, make it um, is it as I said took antibiotic medicine after gut pneumonia. So this is kind of very specific. Um, yeah, yeah, or you cannot use this thing. I don't know. Yeah, you cannot use it probably. That's the best way. One of the way I would probably drop it, or I would create a features that says this is took antibiotic medicine after gut pneumonia. So it's very clear what is this features is referring to. It's like because you have to the timing, the chronological order. Okay. And then the second test leakage is train test contamination. Um, so this is a driven type of leak occurs when you are not careful um, to distinguish training data from validation data. Remember, we have during the training, uh, when we read the data, we want to break it down. Normally, it's 80-20, or depending on how you want to strategize your training. But so far, we are doing 80-20% training and validation. Um, so So recall that validation is meant to be a measure of how the model does on data that he hasn't considered before, right? So the idea why it hasn't considered before, the idea is when you deploy it, when you test it in the real world, then it works, right? Um, you want your model to be generalized. So put that in mind. That's kind of um, the mission, the target is always the algorithm at the end of the day, or the model at the end of the day, has to be generalized. It cannot be just on a specific demographic uh, subset, unless if that's really your intention uh, for your model to be. But for example, if you want to predict the housing, you want to generate the housing market in the whole US, right? But when you gather the data, you only gather the data only from, let's say, Boston area, right? Which is not being represented, right? The whole US, right? So that's not right, right? But if you just want to um, deploy the model on that specific area, then it's fine. Then you just gather the necessary data from that specific area, which is fine. But if you deploy it in a more broader context, then your algorithm become biased, right? So so um, okay, so you can corrupt this process in subtle ways if the validation data affects the pre-processing behavior. Okay, this is called train test contamination. So the validation affects the pre-processing behavior. For example, imagine you run pre-processing, like um, fitting an imputer for missing values before calling train test split. The end result, your model may get good validation scores, um, giving you great confidence, but perform poorly when you deploy it to make a decision. The validation data affects the pre-processing behavior. Um, okay, so when you run the pre-processing, fitting imputer for missing values, okay, it's just so happen that your validation, when they kind of replace that missing values with um, a different, for example, you impute it with mean, or you impute it with the median, or you impute it with the mode. Um, it's just so happen that um, the validation data become kind of not rep, uh, become biased in such a way that um, 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 instead of measuring the model uh, to a data that has not been considered, it's measured again to a data that already has considered. So in another way, your validation data um, mimics the training, or sorry, yeah, the training data, or similar, very similar. So you I mean, there's no point of validating the data after you train it, right? If it's similar, you want it to become kind of completely different. Yet when you validate it, still giving you a good accuracy. It means your model is kind of generalized. But when your validation data is kind of the same, very similar, um, then then when you validate it, it gives you a good um, accuracy or low error because it's kind of the same, right? The train and the validation. And then when you deploy it in the real world, it's so happen because the data is completely like different, then you got poor accuracy. So, so one of the way that you can corrupt if the validation data affects the pre-processing behavior. I think this should be the other way. I think this should be the pre-processing behavior affects the validation data because over here you run the pre-processing, right? Like imputing for missing values before calling train test split, right? So you do something, you pre-process first the validation data, and then you and then you train test split, okay, and then you split it, um, and then the end result, your model may get good validation scores. Huh. Okay. After all, you incorporated data from the validation or test data into how you make predictions. So uh, they may do well on that particular data, even if it cannot generalize to new data. The problem becomes even more subtle and more dangerous when you do more complex feature engineering. Okay, feature engineering is basically just really quick. When you have features, let's for example, talking about the housing again, you have 100 features. Let's say first floor square footage, second floor square footage, it has basement or not, it has swimming pool or not, kitchen square footage, number of bedroom, number of living room, number of bathroom, and so on, right? Feature engineering is just meaning combining, you're making a new features out of the features that you already have. For example, if you have first floor square footage and second floor square footage, probably you can combine that into, let's say, I don't know, main area square footage, right? Or you can combine it into something else. So you're basically creating a new features. Uh, Normally, when you do this, you have kind of an insight how that industry works, right? So you want to consult probably with the domain expertise to do that, right? Um, okay, so when you do this, you might have a train test contamination, meaning it just means your validation data is not kind of is not a good validation data. That's what I'm trying to say. Which means the validation data is kind of very similar to the training data. That's what it means. So that's why when you test it, um, it's not giving you a good result. So that's why it's called train test contamination. So they may do well on that particular data, even if it can not generalize to new data. This problem becomes even more subtle and more dangerous when you do more complex feature engineering. If your validation is based on a simple train test split, exclude the validation data from any type of fitting, including fitting of pre-processing steps. This is easier if you use scikit-learn pipelines. When using cross-validation, it's even more critical that you do your pre-processing inside the pipelines. Okay, I still don't understand this. Why do you um, exclude the validation from any type of fitting? Hmm, I don't understand why. If your validation data, the idea is the validation data has to be kind of different. But isn't it just by putting pre-processing, it still could be different? Yeah, I'm not sure. This is just one of the way. So they recommend to exclude the validation data from type of fitting, so you don't have to pre-process it, something like that. So you just leave it as is, or you kind of like, I don't know what you do with the missing values. You like treat it differently. I don't know. Or you do it after you split the train and test. So over here, when using cross-validation, is even where that you do your pre-processing inside the pipeline. Okay. What does it mean doing pre-processing inside the pipeline? Okay, so in this example, you will learn one way to detect and remove target leakage. Um, okay, target leakage is the one that, the way I understood it is the causal relationship is not interchangeably. Um, we will use a data set about credit card application and skip the basic data setup code. The end result is that information about each credit card application is stored in a data frame X. We'll use it to predict which application were accepted in series Y. Okay, so you have all of this data. Um, so age, income, share, expenditure, owner, self, I don't know what is that, dependent, man, major card. And then you want to predict, for example, in this ID 0, in this row 0, if that person um, will get a credit card or not, will be accepted for a credit card or not. Okay. Since this is a small data set, we will use cross-validation to ensure accurate measure of model quality. Okay, so sklearn pipeline import, make pipeline import random forest, the algorithm, um, the cross-validation score. Since there is no pre-processing, we don't need a pipeline. Use anyways as best practice. What? I don't get this. So make pipeline, random forest classify, and estimator. Okay, there is no pre-processing. Okay, so in the cross-validation score, my pipeline, which is basically just the algorithm itself, and then you put the X and the Y. The X is all of this data set, um, and then the Y is the result, whether it's a credit card accepted or not. The CV is, I don't know what is it, I forgot already. Scoring accuracy. And then after that, you want to get the mean. Oh, I think this is computing for 5 um, different trees, right? I think, and then you average it. So there's going to be like 5 different scores, right? So what is CV? You can check it out really quickly. Random forest classifier. Um, let's see. I think it has to do with the number of trees. CV. CV is um, no, there's no CV here. Probably is on the cross-validation score. Yeah. Oops. What did I do? What did I do? Cross-validation score. What's this? I think it has to do with computing it like 5 times. Cross-validation score. Okay. CV integer determines the cross-validation splitting strategy. Oh, display the possible input for CVR none. To use default threefold. Oh, threefold cross validation. Okay, integer display the number of folds. Okay, so it's the number of folds. Okay, um, got it. So that's the number of folds. The number of section that so you have a data, for example, this big. So if the CV is 5, then it's divided by 5, right? So for so basically it's going to computing 5 times because for each iteration, the cross and the validation is different. So for first iteration, you'll get the first 5 of the data set. The second iteration is the validation is going to get the second of the 5. The third iteration is going to get the third of the 5, and so on. And then it's going to compute all those 5 different cross validation scores. The idea is to make it kind of like uh, balance, I guess, and to make sure um, uh, the the validation data set is using the whole training data set, right? Instead of just a small section, because you want, again, the idea of the validation is you want to have kind of make sure that your validation is kind of different from your training, right? If your validation is the same, then kind of defeat the purpose. So one of the techniques of to make it like different is to break it into chunks. So the first iteration, you just take the first 1/5 of the data set, right? The first row, and then you compute it, and then you take the score, and then you do the second iteration, but this time you take the second, they call it the second fold, right? Hopefully it's going to be different, because if the first fold is the same, then you still have the second fold, right? Which is could be different. So that's the idea. Basically, it is to decrease, I think, the way I see it, the probability of having that your validation data exactly the same as your training data, right? Because you don't want that to happen. Again, if that happens, if your validation is kind of the same, or like 90% the same, or exactly the same, then there's no point of validating your the formula, right? The point of validating your model is to you want to know, to gauge it's how good your model is before you deploy it in the real world. Okay, so I hope I'm making myself clear there. Okay, so we got 0.98. With experience, you will find that it's very rare to find models that are accurate 98% of the time. Okay, it happens, but it's uncommon enough that we should inspect the data more closely for target leakage. Here's a summary of the data, which you can also find under the data tab card. 1 if created application accepted, 0 if not reports. Okay, a few variable look suspicious. For example, does expenditure mean expenditure on this card or on card used before applying? Okay. So average monthly credit card expenditure. Okay. Average monthly credit card expenditure. Yeah. Okay. So that's why it's saying about time, the timing, the chronicle. Is it before or after? Now I get this. Interesting. Because if it's let's say the expenditure, if it's before, then it's a good predictor, right? Because probably the bank wants to kind of approve, or give a chance to approve to people who spend more, right? That is because that's like the bank will be happy because you spend more, then the bank normally get their money, their profits from the interest rate, right? Then you will likely to incur more debt, right, from the bank. Sorry, bank, but that's the way how it works in the real world. and then the bank will be happy. So if it's a before expenditure, right? Then the bank will want to do that. There's, let's say if I spend like $1 million every month before I apply, right? That's good. Um, so discard or on cards used before applying. Okay. At this point, basic data components can be very helpful. Expenditures, card holders. So you'd break it down into two. Okay. Wait. Okay. Fraction of those who did not receive a head sign. Fraction of those who did not receive a card and had no expenditures is 1. Fraction of those who receive a card and had no expenditures is 0.02. Okay, so hmm, expenditure Y. So Y is, what is Y again here? Whether it's the credit card is accepted or not, right? To predict which application were accepted in series Y, okay? Um, so we'll divide it into 2 because we want to know exp expenditure on this card or before applying. So fractions who did not receive a card and had no expenditures. Fraction who received a card and had no expenditure. Okay. As shown above, everyone who did not receive a card um, had no expenditure. Okay, only 2% of those who receive a card had no expenditures. So it's very small percentage. Okay, because if um, if you don't have any expenditure, then most likely, like 98% of the time, um, I think what is this saying is if you don't have any expenditure, 98% um, you won't receive a card. But the one over here is saying that if you had no expenditure, um, no, sorry, everyone who did not receive a card had no expenditures. Okay. It's not surprising that our model appeared to have a high accuracy, but this also seems to be a case of target leakage, where expenditure probably means expenditures on the card they applied for. Kind of confused with this. Since share is partially determined by um, expenditure, it should be excluded too. Share? What is share? Is there share here? Ratio of monthly credit card expenditure to yearly income. Share, okay. Ratio of monthly credit card expenditure to yearly income. Okay, so for example, if you spend $1,000, or let's just say $5,000, and if you have a yearly income of 50,000, that means you have a 10% share, right? Ratio. Okay. So what do you do? Let's see. Since share is partially given, it should be excluded. So you want to exclude it. Okay. The variables active and major car are a little less clear, but from the description, they sound concerning. In most situations, it's better to be safe than sorry if you cannot track down the people who created data to find out more. We would run a model without target leakage. Oh, okay. So yeah, this is what I thought. You just drop it because the relationship is not vice versa. Yeah, means it's only um, true. Um, how do you say it? Uh, I couldn't explain it. So you identify the potential leaks. So there's four: expenditure, share, active, major cost, and then you drop it. Okay. And then now you have much lower after you drop it, right? But that's at least um, your algorithm doesn't overfit. Um, but this is not because of the choice of algorithm or the parameters is not like kind of like tuned properly, but this is more because of um, the features um, are not supposed to be included during the training and the validation. Yeah, because uh, how do I? It will skew the result. Yeah, that features. So you cannot drop it. Yeah, yeah. Okay. So the accuracy is quite a bit lower, which might be disappointing. However, we can expect to be right about 80% of the time when used on new application, whereas the leaky model would likely do much worse than that, in spite of its higher apparent score in cross-validation. Okay. Conclusion, data leakage can be a multi-million dollar mistake in many data science applications. Careful separation of training and validation can prevent train test contamination, and pipelines can help implement this separation. So you have to separate between the training and the validation data. Careful separation because you want to make sure your validation data is kind of completely different from the training. Like, why is a combination of caution, common sense, and data exploration kind of identify target leakage? Yep. Is this true? This may still seem abstract. Try thinking through the example in this section to develop your skill and evaluate target leakage and train test contamination. Okay, so okay, I'm trying to understand this one more. So we are dropping this thing because we suspect that especially the expenditure, um, for example, okay, so um, we do not know if this is um, expenditure before or after you apply expenditure on this card or on card use before applying. Yeah, yeah, because you could like yeah, because you want it to be expenditure on cards before applying, right? Because if you put expenditure on this card, which happens after um, after you got the card, after you being approved, right? Then it doesn't make sense to be included, right? Yeah, because you want to use, remember, you want to use your formula to predict, right? So in other words, I think there's a sequence here. That's why it says important. There's a time, there's a chronological order. So if you want to predict, let's say, the sale price of the house, um, all of the features that are included there, right? That are included um, to determine the sale price of the house, whether it's how big is the first floor square footage, how the second footage, whether it has a kitchen, right? That all of that features uh, makes sense to be included only if that helps to determine the sale price, right? You want to predict. But in this case, there is this features called expenditure, and we want to predict if uh, he can get a credit card or not, right? So there's a um, kind of uh, causal relationship, right? So if you have, for example, expenditure of this much, right, then you can be approved. But again, over here, I think the expenditure is not what the data, the this session is, uh, this Kaggle is trying to say that it's not clear. What if the expenditure is after um, that person got the credit card, right? Then it doesn't make sense, right? So, for example, if you ask the person, okay, you ask me, say, for example, for MasterCard, okay, I got MasterCard, which means it's yes. And then they ask me, what is my expenditure, right? And it's like fake. So I don't know what is he referring my expenditure like before I got the credit card or after credit card. And then I said, for example, I said after, for example, my expenditure is, I don't know, $5,000 a month, something like that. Um, right. So that data is kind of meaningless the way I see it, um, because it happens um, after I got the card. So whatever after, it's kind of meaningless. You need to know kind of before that because you want to predict, right? So the same thing as the housing. Whatever after, let's say the housing of the sale price, probably you want to include, I don't know. Yeah, okay. So you want to include, what is it? What's a good um, whether that person um, is a lawyer or not, for example. It has nothing to do with um, the sale price of the house. Okay. Anyway, um, yeah, just think about this. I'm gonna think about this again. It's been an hour, so I have to end this now. Uh, but this is a really interesting case to think about the data leakage. So this reading makes me realize that I have to be careful about the chronological time. So that's why it says here, up here, it says about the time. So um, if you have the moment of prediction here, before that is usable. But whatever happened after that moment of prediction is not usable. So for example, in the house, I'm trying to give an example of the housing data set, using the housing data set example. So for example, if you already build a house, you already determine the price of the house. For example, the house is being built 1980s, right? And then example is $1 million, right? And then after that, 1980s, let's say 1981, there is a, I don't know, because of the house, there is a, for example, um, uh, data set about how about cars, the number of cars. But that happens after that house being built. So we include that data. Let's say the number of cars becomes 10,000, but that happens, let's say after 1981. Let's say it's 1990, it's become 10,000. So um, yeah, so in a way that data doesn't make sense to be included, um, and it's just gonna corrupt the data. So that's why, okay, so that's why this makes sense. You have to exclude uh, every data that's being generated after that, the prediction you want to predict. So for example, in the case of predicting the card, if there is an expenditure, that expenditure has to be before he got the card, not after he got the card. Okay, now that makes sense. So hopefully that kind of click, it's kind of clicking on me. Let me know about your thoughts, because this is a really important um, uh, um, session about data leakage. And next time I'm gonna go through the exercise, and my guess is gonna take a long time to do the exercise, because yeah, it's kind of very you kind of like really try to think through of this. All right, I'll see you next time. Thanks for listening. Please give thumbs up if you like it. If you don't like it, please give a construct criticism. Anything I can do better. Hopefully, I can deliver that. Until next time, and happy machine learning. Bye. Stop this one.